Ethereal music plays as the title, cutting-edge scientific theories, appears on screen with a backdrop of cosmic imagery and mathematical equations, floating in space 00:30. Welcome to Module 8 of our Unusual Science series, where we venture into the realm of theoretical concepts. I'm your guide into the perplexing frontiers of human understanding. Today, we'll explore cutting-edge scientific theories that challenge our fundamental perception of reality itself. These aren't merely academic exercises, they're potential keys to unlocking the deepest mysteries of existence. 0:30:115. What is reality? Is the universe as we perceive it merely an illusion, a shadow play of deeper, more fundamental processes? The theories we'll explore today suggest that reality may be far stranger than even our wildest imaginations. From vibrating strings smaller than atoms to the possibility that our entire universe is a holographic projection, these theories push the boundaries of what we consider possible. 1:15:20, the renowned physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." If that was true of quantum mechanics, a well-established field, imagine how much more mysterious these newer, more radical theories must be. Yet these cutting-edge ideas may hold the key to unifying our understanding of the cosmos, from the smallest subatomic particles to the vast expanses of intergalactic space. 2:02:45. As we journey through these baffling concepts, I invite you to embrace the enigma, to find comfort in the discomfort of not knowing. For it is precisely at the edges of our understanding where the most profound discoveries await. Let us begin our exploration of 5 cutting-edge theories that may fundamentally reshape our scientific worldview. Image transitions to vibrating strings in multiple dimensions, with complex mathematical equations appearing alongside them. 2:45:330. Our first venture is into the enchanting realm of string theory, an idea that first emerged in the late 1960s but continues to evolve in bewildering new directions. At its core lies a deceptively simple premise: all fundamental particles are not point-like dots, but rather tiny, one-dimensional vibrating strings. Like the strings of a cosmic instrument, each particle, be it an electron, a photon, or a quark, represents a different vibrational pattern of these fundamental strings. 3:34:15. But here's where reality begins to unravel before our eyes. These strings don't vibrate in our familiar three-dimensional space. They require additional dimensions, typically 10, 11, or even 26 in various formulations. These extra dimensions, curled up into impossibly small configurations called Calabi-Yau manifolds, exist all around us yet remain utterly invisible to our limited perceptions. 4:15:50. The mathematical beauty of string theory is both its greatest strength and its most perplexing challenge. Edward Witten, one of the theory's foremost proponents, described it as a piece of 21st century physics that fell by accident into the 20th century. Its equations reveal a universe of such staggering complexity and elegance that many physicists find it difficult to believe it could be wrong, yet equally difficult to prove it right. Visual shifts to show multiple parallel membranes, branes, with strings connecting between them. 5:05:45. String theory has evolved into what we now call M-theory, where M stands for membrane, magic, or mystery, depending on whom you ask. M-theory introduces objects called branes, multidimensional membranes that could represent entire universes parallel to our own. Imagine our universe as just one of many cosmic sheets floating in a higher dimensional space, with gravity able to leak between these separate realities. 5:45:630. The implications are nothing short of revolutionary. String theory offers the tantalizing possibility of explaining all fundamental forces, gravity, electromagnetism, and the nuclear forces, as different manifestations of the same underlying phenomenon. It might also explain the apparent weakness of gravity compared to other forces, as its influence could be diluted across multiple dimensions. 6:37:15. Yet, for all its mathematical elegance, string theory faces a profound experimental challenge. The energies needed to directly observe these strings would require particle accelerators the size of galaxies. Critics argue this makes the theory unfalsifiable and therefore not truly scientific. proponents counter that indirect evidence may eventually emerge, perhaps through astronomical observations or unexpected patterns in particle physics experiments. 71580. If string theory ultimately proves correct, it would represent perhaps the greatest unification in the history of physics, revealing our universe to be an intricate symphony of vibrating strings, playing out across dimensions we can barely conceive. Visual representation of quantized spacetime as a network of interlocking loops and nodes 80845, while string theory has captured much of the public imagination. Another equally revolutionary approach silently waits in the wings: loop quantum gravity. This theory takes a fundamentally different approach to unifying quantum mechanics and general relativity. Instead of adding more dimensions, it suggests that space itself is not continuous but quantized, composed of discrete units at the smallest scales. 845-930 Imagine spacetime as a vast network of finite loops, each representing a quantum of space approximately 10 meters across, the infamous Planck length. These loops interconnect to form what physicists call a spin network, a quantum version of Einstein's spacetime. In this view, space is not an empty stage upon which matter performs, but rather an active participant in the cosmic drama, a dynamic web of relationships between quantum entities. 930-1015. One of loop quantum gravity's most intriguing predictions concerns black holes, those cosmic enigmas where spacetime appears to fold in upon itself. The theory suggests that as matter collapses, it reaches a point where quantum effects prevent further compression. Instead of a singularity of infinite density, there would be a quantum bounce, potentially creating a new expanding region of spacetime, perhaps even a new universe. 1015-11-0 Carlo Rovelli, one of the theory's architects, poetically describes it as revealing that the solidity of the world is an illusion. There is nothing in reality that is fundamental. Everything emerges from a boundless web of connections. If correct, loop quantum gravity would completely transform our understanding of space and time, revealing them to be emergent properties of a deeper quantum reality. 11-0-11-45 The experimental validation of loop quantum gravity presents formidable challenges. Yet some researchers believe that radiation from the early universe might bear imprints of this quantum spacetime structure. Others suggest that high-energy cosmic rays might interact with this quantum foam in ways that could be detected by our most sensitive instruments. Visual of a hologram with a 3D universe emerging from a 2D boundary. With mathematical equations flowing between dimensions, 1145-1230, our third theory ventures into territory so strange, it seems to defy common sense entirely. The holographic principle. Imagine if our three-dimensional reality, with all its complexity, all its depth, were merely a projection of information stored on a distant two-dimensional surface, much like a hologram creates the illusion of depth from a flat image. 1230-1315. This mind-bending concept emerged from the study of black holes, when physicists realized that the information content of a black hole appears proportional not to its volume, but to the area of its event horizon. This suggests a fundamental principle. The maximum information content of any region of space is limited not by its volume, but by its boundary surface area. 1315-14-0, extending this principle to its logical conclusion, leads to an astonishing possibility. Our entire universe might be encoded on a distant two-dimensional boundary, perhaps at the edge of the cosmos itself. Everything we experience as depth, as three-dimensional reality, would be an elaborate projection of this boundary information. 14-0-1445 This isn't merely philosophical speculation. The mathematician Juan Maldacena formalized this idea in what's called the ad-SCFT correspondence, a rigorous mathematical relationship showing how a theory of gravity in a space with particular properties corresponds exactly to a quantum field theory without gravity on that space's boundary. 1445-1530, if the holographic principle is correct, it would represent one of the most profound shifts in our understanding of reality since Copernicus displaced Earth from the center of the cosmos. As physicist Leonard Susskind puts it, the three-dimensional world of ordinary experience, The universe filled with galaxies, stars, planets, houses, boulders, and people is a hologram, an image of reality projected from a distant two-dimensional surface. 1530–1615 recent experiments have found tantalizing hints that might support this principle. Researchers have discovered quantum entanglement patterns that match holographic predictions, and some suggest that certain unexplained cosmic observations might find their resolution in this framework. The universe, as a hologram, perhaps the ultimate example of reality being stranger than fiction. Visual showing galaxies with altered gravitational effects, alongside equations showing modified gravitational laws. 1615–17 our fourth venture, takes us into territory that challenges perhaps the most successful physical theory ever developed: Einstein's general relativity. For all its confirmed predictions, from gravitational waves to black holes, Einstein's theory faces persistent anomalies when applied to galactic scales. Enter modified gravity theories, approaches that dare to ask, what if Einstein's equations need revision? 1745. The most prominent of these theories is MOND, modified Newtonian dynamics, which proposes that gravity behaves differently at extremely low accelerations, such as those found at the edges of galaxies. Where conventional physics invokes invisible dark matter to explain galactic rotation, MOND suggests the laws of gravity themselves change at these scales, eliminating the need for exotic unseen matter. 1745–1830. Similarly, alternatives to dark energy, the mysterious force apparently accelerating cosmic expansion, have emerged. Theories like FR gravity modify Einstein's field equations to produce cosmic acceleration naturally, without requiring an enigmatic energy permeating empty space. 1830–1915, these approaches remain controversial. Observations like the bullet cluster collision seem to provide direct evidence for dark matter's existence. Yet proponents of modified gravity continue to refine their models, seeking the crucial observation that might definitively settle this cosmic debate. 1915–20, recent theoretical developments have produced theories that might explain both galactic rotation and cosmic expansion without dark components, while still preserving Einstein's successes on solar system scales. If any of these theories ultimately proves correct, it would represent a paradigm shift comparable to Einstein's original revolution, revealing that our understanding of gravity, the most familiar of forces, remains profoundly incomplete. Visual showing nested simulations, with binary code transitioning into increasingly complex realities. 2045, our final theoretical frontier, may be the most philosophically unsettling of all: simulation theory. This hypothesis proposes that our entire reality, all we see, feel, and experience, might be an elaborate computer simulation created by an advanced civilization. While this might sound like science fiction, a growing number of physicists, philosophers, and computer scientists take the possibility seriously enough to develop testable consequences. 2045–2130, the argument, most famously articulated by philosopher Nick Bostrom, runs as follows. If advanced civilizations can create simulated realities indistinguishable from base reality, and if they would create many such simulations, then simulated realities would vastly outnumber the single base reality. Statistically speaking, we would most likely exist within one of these simulations rather than in the original reality. 21–30–22–15, some physicists, including Silas Bean of the University of Washington, have proposed that a simulated universe would contain detectable artifacts, computational shortcuts or limits that might reveal its true nature. These could include a fundamental minimum length scale, unexpected patterns in cosmic rays, or certain quantum field behaviors that would be computationally efficient to simulate. 22–15–23 others have suggested that the digital nature of quantum mechanics itself, the fact that energy and other properties come in discrete packets rather than continuous streams, might be evidence of an underlying computational reality. After all, discreteness is a hallmark of digital systems, where continuous functions must be approximated by finite steps. 23–2345 Elon Musk famously suggested that the chances we're living in base reality are 1 in billions. Yet others, like physicist Sabine Hossenfelder, caution that simulation arguments often misunderstand the nature of computation and physical law. Nevertheless, the question remains open, and some researchers continue to develop experimental tests that might reveal whether our reality is rendered rather than fundamental. Visual showing all 5 theories interconnected in a conceptual web, with images transitioning between them 2345, 2430. As we've journeyed through these 5 cutting-edge theories, you might wonder, can they all be correct? The answer is both yes and no. These theories often overlap in fascinating ways. The holographic principle finds natural expression within string theory. Simulation theory might explain why quantum mechanics resembles computational algorithms. Modified gravity might be a consequence of extra dimensions. 2430, 2515, yet they also represent fundamentally different approaches to reality's deepest mysteries. String theory adds dimensions. Loop quantum gravity quantizes space itself. Modified gravity alters Einstein's equations. The holographic principle recasts them in lower dimensions. Each approach offers unique insights, and the ultimate theory might incorporate elements from several of these frameworks. 2515, 260, what unites these disparate theories is their radical challenge to our conventional understanding of reality. They remind us that our perceptions evolved to navigate the mesoscale world of predators, prey, and tribal politics, may be woefully inadequate for grasping the fundamental nature of existence. As Arthur Eddington once remarked, not only is the universe stranger than we imagine, it is stranger than we can imagine. 260, 2645, yet through mathematics, the language that seems uniquely capable of transcending human cognitive limitations, we continue to probe these enigmas. Each equation is like a spell cast into the darkness, occasionally conjuring unexpected revelations that transform our cosmic understanding. Visual showing the evolution of physics theories throughout history. With these cutting-edge theories at the frontier 2645, 2730, the history of science teaches us humility. Theories once considered unassailable, from geocentrism to Newton's absolute space and time, have given way to deeper understandings. The cutting-edge theories we've explored today may suffer similar fates, or they may prove to be profound insights that revolutionize our worldview. The only certainty is uncertainty itself, the perpetual frontier where true discovery occurs. 2730, 2815, these theories also blur the traditional boundary between physics and philosophy. They raise profound questions about the nature of existence, consciousness, and reality that transcend purely scientific inquiry. Are we three-dimensional projections of two-dimensional information? Are we vibrating strings in an 11-dimensional cosmos? Are we simulated beings in a computational universe? Science approaches these questions with mathematical rigor, but the implications extend far beyond equations. 2815, 290, as we stand at the precipice of these mind-bending possibilities, we might feel a certain vertigo, a dizzying sense that reality itself is slipping through our fingers. Yet there is profound wonder in this uncertainty. We are participants in the greatest intellectual adventure imaginable, the quest to understand the fundamental nature of existence itself. Visual returns to cosmic imagery with the title Cutting-Edge Scientific Theories, and a preview image for weird quantum phenomena, 2945 in our next lecture. We'll delve into the equally perplexing world of weird quantum phenomena, the experimentally verified strangeness that underlies these cutting-edge theories. We'll explore quantum entanglement, superposition, tunneling, and other bizarre behaviors that defy classical intuition, yet form the foundation of our modern technological world. 2945, 30. Until then, I encourage you to dwell in the mystery, to sit comfortably with not knowing. For as the physicist Werner Heisenberg reminds us, the first gulp from the glass of natural sciences will turn you into an atheist, but at the bottom of the glass God is waiting for you. Thank you for joining me on this journey into the unknown frontiers of scientific understanding. Ethereal music fades out as the credits appear.